Greetings, everyone. My name is Agaba Lucky, and I'll be taking us through a review of the paper on road terrain recognition based on tire noise autonomous vehicle. So let's get started. Effective road terrain recognition is crucial for enhancing the driving safety, passability, and comfort of autonomous vehicles. This study basically addresses the challenges of accurately identifying diverse road surfaces using deep learning in complex environments. And at the same time, it introduces an end-to-end tire noise recognition residual network model integrated with a time frequency attention module designed to capture and leverage time frequency information from tire noise signals for road terrain classification. The method was evaluated on 5 distinct road types, that is asphalt, cement, grass, mud, and sand. So the performance of this tire noise recognition residual network, or in short, TN ResNet, was rigorously compared against traditional machine learning techniques, including decision trees, k-nearest neighbors, and support vector machines, as well as advanced deep learning models like the long short-term memory and convolutional neural networks. Experimental results basically demonstrate that the TN ResNet achieves superior classification accuracy of about 99.48%. And according to the paper, this outperforms all comparative methods. And this work not only establishes a robust framework for road terrain identification, but also it showcases the significant practical implications of TN ResNet in the realm of autonomous vehicle navigation. Therefore, for this particular paper, it introduces the deep learning-based tire noise recognition residual network designed to improve the accuracy of road terrain recognition for autonomous vehicles. And it conducts a series of experiments to evaluate the TN ResNet's performance across various road types, including asphalt, cement, grass, mud, and sand at different speeds. And the comparisons include established methods such as decision trees, k-nearest neighbors, support vector machines, long short-term memory, and conventional CNNs, ensuring a comprehensive assessment. The paper puts it that the results reveal that TN ResNet significantly outperforms comparative methods, achieving an average classification accuracy of 99.48%, which is markedly higher than the best performance recorded for SVM, KNN, and decision trees. Let us look at the model architecture. The TN ResNet model is an innovative adaptation of the ResNet 1825 architecture tailored for road terrain classification tasks. And the architecture consists of 5 blocks. The initial block includes a convolutional layer with a kernel size of 7 by 7 and a stride of 2, followed by a batch normalization layer and a ReLU activation function. And this block is crucial as it extracts initial features from the input MER spectrograms, enhancing the model's ability to discern intricate patterns in the data. And the remaining 4 blocks are structured as residual blocks, each containing 2 basic blocks. Then also each basic block consists of convolutional layers with a 3 by 3 filter size and a stride of 1. The residual connections in these blocks allow for more effective training by mitigating the vanishing gradient problem, thus improving model convergence. Then also, the design rules followed are that when the output feature maps size matches the input, the number of filters equals the number of input feature maps. Then also, another one is that when the output feature map size is halved, which is achieved using convolutional layers with a stride of 2, the number of filters is doubled. That implies that each convolutional layer is succeeded by batch normalization and ReLU activation layers. Additionally, there was an implementation of a time frequency attention layer to effectively extract and emphasize time and frequency information from the input feature map. And this basically contributed to the model's adaptability to varying conditions. The time frequency attention proposed a time frequency attention module inspired by the convolutional block attention module for a given input feature map. And also the time weight feature map focuses basically on the meaning moments for a given input feature map and can be generated by utilizing the intertime relationship of feature map. They first applied average pooling operation along the frequency axis to reduce parameter overhead. They also applied a one-by-one kernel size convolutional layer for reducing dimensions to produce a feature map. And a batch normalization and ReLU activation function followed by the one-by-one kernel size convolutional layer. And then these were concatenated on the concatenated feature descriptor. They applied a 3x3 kernel size convolutional layer and sigmoid activation function to generate a time-weighted feature map. This paper also has an experiment kind of it, the experiment which were carried out to get the results. As it was suggested by some of the researchers, the testing vehicle was instrumented with a single microphone installed on the front wing of the right rear wheel proximity, which permits to achieve a better signal to noise ratio. And this prevents noise disturbance from the vehicle's engine, exhaust pipe, and other parts. In addition, to avoid the influence of wind, a windscreen was used for the microphone, and they also used the microphone with 44.1 kilohertz sampling frequency to collect tire noise signal driving on asphalt road, cement road, mud road, grass road, and sand road. And the driving speed was controlled from 10 to 80 kilometers per hour with a 10 kilometer per hour interval. And the time length for different roads under varying speed segments were also observed according to the paper. Then the experimental results analysis were that the comparison of TN-ResNet with the traditional machine learning methods such as decision trees, KNN, and SVM, and other deep learning models, including the LSTM and CNN, highlight its significant advantages and innovations in diverse conditions. In the evaluation against machine learning approaches, TN-ResNet demonstrates a remarkable improvement in road surface recognition tasks, and the decision tree model achieves a maximum validation accuracy of 82.7%, while the KNN and SVM attain a maximum accuracies of 78.7 and 86.8% respectively. However, the TN-ResNet or the tire noise recognition residual network surpasses all these methods, illustrating its effectiveness in complex pattern recognition. Therefore, specifically, TN-ResNet outperforms the decision tree, the KNN, and the SVM by enhancing average, precision, recall, and F1 scores. So when compared to deep learning models, TN-ResNet continues to excel. It consistently achieves superior performance across various evaluation metrics compared to LSTM and CNN. Notably, TN-ResNet shows improvements of 3.0, 3.2, and 3.1 in average precision recall and F1 score, respectively, over the LSTM. And this enhancement underscores the TN-ResNet's unique architecture in feature extraction and pattern recognition. making it more reliable for complex applications such as autonomous driving. Then also, the TNS resonance design not only exhibits superior accuracy, but also demonstrates exceptional adaptability. Its multi-layer network architecture effectively processes tire noise signals in varying environments as validated by the experimental results. Whether on sandy, muddy, or concrete surfaces, TNS Resonate consistently displays high stability and accuracy. This adaptability meets the requirements of autonomous driving systems in dynamic environments, thereby improving driving safety and decision-making efficiency. Therefore, this paper basically addresses key considerations regarding the TNS Resonate model's applicability, computational efficiency, and generalization capabilities for road terrain recognition in autonomous vehicles. And one of the critical aspects of the TNS Resonate's long-term viability is its operational stability and adaptability under varied environmental conditions. And regarding the computational efficiency, the demands of the TN Resonate on edge devices, typical in autonomous vehicles, necessitates further discussions or further research. Strategies such as model pruning, quantization, and knowledge distillation can be employed to optimize the network for real-time processing, effectively reducing computational load while maintaining the performance. Also, the experimental validation of TNS Resonate currently focuses on 5 common road surfaces, which limits its robustness demonstration. To enhance the model's applicability, the researchers recommend conducting additional tests on more challenging terrains, including snow, ice, and gravel. This diversity in terrain types will provide a more comprehensive understanding of the model's generalization capabilities. Whereas the findings highlight the strength of TN Resonate, it is essential to acknowledge its limitations. The model's performance on unmarked and degraded road surfaces has also been inconsistent, this therefore suggesting a potential lack of generalization in unfamiliar conditions. Therefore, expanding the training datasets to encompass a wider range of terrain types and employing transfer learning techniques could enhance its robustness and adaptability. Some of the key areas of research is in future would be analysis of misclassification, basically conducting a thorough analysis to understand the causes of misclassified data, leading to targeted improvements in data preprocessing and model optimization. Then also environmental adaptability testing. That includes regularly implement environmental simulation tests to prepare the model for diverse operating conditions, ensuring better performance in real-world scenarios. Then also resource optimization research. There is a need to explore efficient computation techniques specifically designed for autonomous driving systems to align the model's requirements with the computational constraints. Then also enhanced of generalization skills. There is a need to expand the training datasets to include a broader variety of road conditions and investigate machine learning techniques that support better transferability and learning from sparse data environments. So by addressing these 4 considerations, we can aim to enhance the TN Resonate model's effectiveness and reliability in real-world autonomous driving applications. That's what I had for now. Be blessed.